Hi, we're going to talk about a specific heat lab. So in this lab, it is taking a hot metal and putting it into cold water for the purpose of finding the specific heat constant for the metal. So there are really two parts to this. First, you have to collect data with hot and cold water in order to find the calorimeter constant. So I have a couple of things here to show you. Here are nesting cups. See that there are two cups. So you put two of the styrofoam cups together, double insulation. And here's the question. For every degree that you increase the temperature of that cup, of the solution in the cup, how much energy does that cup absorb? So remember, if I'm pouring, let's say I have cold water in here, hot water into this, that hot water is exothermic, is going to release its energy, but the energy goes two places. It's going to go into the cold water and into the cup. And we want to figure out what's the rate at which that energy is absorbed. So how much energy is absorbed for every 1 degree C change. So that's going to be part one. Now part two is finding the specific heat of the metal. And we're going to do that by taking a hot metal and putting it into the cold water. So two things. We're going to look at the very tactile, tangible, what you're going to be doing in the lab, number one, and then number two, we're going to look at the math. So let's talk collecting data. This is a hurry up and wait lab. First thing that you're going to do is get water boiling, and I suggest do some multitasking. I would carefully put your metal ingot, this happens to be copper, I put the metal ingot in the beaker, fill it with water, and get that on your hot plate warming up as soon as possible. The most time-consuming aspect of this lab is waiting for water to boil. So you're going to get this water boiling. Now, while that is happening, you can get regular water, doesn't have to be distilled water, just tap water. I would measure out 50 mils of water. So you'll recall that the density of water is 1 gram per mil. So if I have 50 mils of water, you're going to have 50 grams of water. Now just a reminder, be really careful on sig figs. This particular graduated cylinder, let you see that close, reads to the ones place. So 50, 51, 52. That means you have to make a guess in between those graduated marks. Your guess is going to be at the 10th place. So if spot on, that meniscus is hitting the bottom, or the bottom of the meniscus is hitting that 50 mil, then you would say 50.0. Your guess is the 0.0 of the 10th place. So just be sure that you make that guess on the 10th place. So let's say that we fill up our graduated cylinder with 50 mils of water. I'm going to pour it into my graduated cylinder. Now we're going to get a temperature probe. Here we go, and I'm going to put it in here, get the temperature of the cold water. So we will have then for our cold water, the mass, 50 grams, and the initial temperature, let's pretend that it's 22 degrees C. Okay, now for the hot water. Let's say that the hot water is boiling. You're going to get a silicone glove, or if you have beaker tongs, whatever is available so you don't get burned. Okay, so you're going to pick this up off of the hot plate, and you are going to pour 50 mils of hot water into the graduated cylinder. Now be careful, when you pour in here, don't be holding the bottom of the graduated cylinder. It will burn your hand. So hold up here, and you're carefully going to pour that hot water until you get the 50 mils hot water. Now the instant that hot water goes into the graduated cylinder, it begins to cool down. So if you have a couple of people in your lab, this works best. If not, you're just going to have to be super efficient and as fast and accurate as possible. You're going to take the temperature of the hot water in the graduated cylinder, and then as smoothly and quickly as possible, you take that temperature probe out and you pour the water, the hot water, into the cold water. At that point, get another cup and cover it up. We're trying to avoid losing energy to the air. We want all the energy to go into the cold water and into the cup. Now, this is something good to report in your evaluation. So you'll write your conclusion, this is what you learned, justified by the data, and then in your evaluation, where were the limitations, where were the errors? This whole process of pouring into here, you're going to lose energy, and it's going to create error inside of your lab. So what could you do to minimize that if you redid the lab? Okay, so while this is here, What I recommend to my students, if you have a hot plate or a magnetic stir that hasn't been used, not warm, you could set that on the hot plate and let it stir. Or because our hot plates that we're using in our classroom, they are already hot, we can't use the magnetic stir. I have my students kind of make a little hole in the cup and have them stir. So they're waiting and they're observing that the temperature is going up, up, up. This cold water is going from 22 degrees, goes up, 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 until it levels off at 48 degrees. So that's your thermal equilibrium, the highest temperature that it reaches. And remember that that thermal equilibrium, that's the final temperature for both the hot water and the cold water. And we would have recorded what the temperature was when we took the temperature of the hot water in the graduated cylinder. Okay, notice the specific heat of water is the same. It's one of the reasons why we use hot water and cold water, is because we know the specific heat of both of these. So let's take just a second and look at the math. The hot water is exothermic, releasing energy. And all the energy, we're saying, all the energy released by that hot water is going in two places. It's going to go into the cold water and it's going to go into the cup. So you're going to have negative Cm delta T of the hot water. Be really careful with that negative. Remember, you have to carry it mathematically. Equals Cm delta T of the cold water plus K, the amount of energy absorbed by that cup, is the calorimeter constant times delta T. And just a little reminder, that's the same change in temperature as the cold cup. When you put the cold water, when you put the cold water in here, the cup comes into thermal equilibrium with the cold water. So delta T with the calorimeter constant is the same as the cold water. Okay, you plug in all of those numbers. If you need to take a second, pause it and look at the numbers to be sure that you understand where we went from the data that you record to the calculation. And show your teacher all of your work, have that nice clean data table, and then have the really nice clean calculation. The calorimeter constant came out to be 169 joules per degree C. It's reasonable, I tell my students, for styrofoam cups to have a calorimeter constant anywhere from 30 joules per degree C to 200. If you're beyond that, I would do it again. I would run it again. And in fact, there are some teachers that will have you do 2 trials on this for the calorimeter constant every time. It's a good practice. I don't make my students do it because of the length of our class period. Okay, now, so we have the calorimeter constant. Now we've got to figure out the specific heat of the metal that's inside of here. So remember, we put this whole thing on the hot plate to warm up. As soon as this starts boiling, I would set your timer for 10 minutes. Okay, now this metal, for that metal all the way down into the center, for every atom to come into thermal equilibrium with the boiling water, it needs to boil for at least 10 minutes. So as soon as it starts boiling, set your timer for 10 minutes. Now at the 10 minutes, that's when this is in thermal equilibrium with the boiling water. So what you're going to do, you will take tongs. First, okay, it's boiling. It's been boiling for 10 minutes. So you're going to put your temperature probe in there, get the temperature. Where we live, the boiling point, because of we're at a really high elevation, is going to be about 95 degrees, okay? So it's boiling, it's about 95 degrees C. Write that down. That's going to be the temperature of the metal. It's in thermal equilibrium with that boiling water. Then you're going to take tongs and, okay, before we can put tongs, use the tongs to put the metal in here, you got to put new cold water in here. So you dump out all that water. Dump out that cold water mixture here. Okay, start over. And I have had students make this mistake. Dump out this water. Okay, so I dump that water out. We start new. Get your 50 mils of tap water, pour it in here, and take the temperature of the cold water. So, all right here, specific heat of water, initial temperature, we're going to say is 22. You've got 50 grams of water. Then you're going to take your tongs. Sorry, I don't have tongs with me right here. Take your tongs from the boiling water, and again, you're going to do this as fast as possible. So pretend my hand is the tong, okay? you go out, and I would have, with your tongs, I'd have this cup as close as possible, because we don't want to lose the energy from that metal into the air. And you put it as fast and carefully as possible into the cold water, the cup, and then cover that up again. Same thing, take your temperature probe, you're going to put this in here. I tell my kids to stir it as much as they can, trying to move that water around. And you're going to notice that the temperature goes up. Now the temperature is going to go up considerably less than when you added hot water and cold water. So don't be surprised by that. Now I made up all of these numbers. I said that this rose from 22 to 24.5 degrees C. And we had weighed this. Oh, that's another really good thing. Make sure that you weigh your ingot before you put it in the beaker, because you don't want to have any water on this when you weigh it. It will definitely skew your results. So weigh this first before you put it in the beaker to boil. Now, once you reach that thermal equilibrium, you can, it depends on what your teacher's going to have you do. I have my students do at least 2 trials, and it kind of depends on the time of the class. Once you have this in here, you reach thermal equilibrium. If you have to do a second trial, as fast as you can, put it back into that boiling water with tongs, carefully set it in there, and you got to let it boil another 10 minutes to get that second trial. Okay, let's look at the math together. So all of that energy from the metal is going to release into the water. So the energy released from the metal goes into both the water and the calorimeter. So you have negative Cm delta T of the metal equals Cm delta T of the water plus the calorimeter constant times the change in temperature. And again, that change of temperature for the calorimeter constant is the same as the cold water. Plug everything in. We're looking for the specific heat of the metal. That's your unknown. Be really careful with that negative. Carry it mathematically. And I wanted to point out the calorimeter constant. That's what you got from this data and the equation. You found the calorimeter constant. So that 169 joules per degree C goes right there. So you're going to use your calorimeter constant in this. Solve for this, we've got the specific heat of the metal is 1.34 joules divided by gram times degree C. Again, I made up these numbers. A metal will always be less than 1, so this is a little garbage data, but it shows you how to do it mathematically. Last thing I'd recommend is, if you know what this metal is, and my students, I let them know what the metal is, look up the actual specific heat, and then you can do the percent error. So what the actual is minus your experimental. If you're doing 2 trials, average the specific heat of the 2 trials and put that there for your experimental. Divided by the actual times 100, and that will give you percent error. I've had as good as 2% in the lab from students and as bad as 250% in the lab. It's really the transfer of the hot water and the hot metal to see how good you do. Let's see here. So specific heat for a metal, 2 basic things: calorimeter constant and finding the specific heat of the metal. So hurry up and wait. As long as you understand this, you get water boiling as fast as possible, the lab should go really smooth. Good work and have a wonderful day.